Hello everyone, welcome back. And at the end of the last video, I was just talking about where these two are going to go. So again, if these three arch nemesis or whatever you want to call them, are enemies, are wanting to get away from each other as much as possible, then these two are going to move. And they're going to move down away from this one, but they're not going to want to get too close to each other. So they're going to have to get as far apart from each other as possible. And what's going to happen is then these guys are going to move down, and they'll be somewhere down here. So you've got this one down here, maybe this one down here. And so they will be equidistant from each other. So the distance between all of them should be the same, or the angle between them is going to be the same. So if you think of this as a pie, then you have three pieces that are cut. So then here the angle would be 120 degrees. So the 120 degree angle between them. So 120 degree angle. Here the angle is 180 degrees. Okay, so that is my analogy. So let's look at a couple of molecules. So if I look at a couple of molecules here, if I draw the Lewis dot structures. So the first one is going to be BF3. So boron is your central atom, and then I have fluorine, and fluorine. Or you could draw it like this. You could draw the Lewis dot structure like this, right? So you could draw it like this, right? So one of the things I want to mention about Lewis dot structures is that the Lewis dot structure is not going to necessarily show you the shape of the molecule unless you draw it that way. But you don't need to draw it that way. Lewis dot structures are not meant to show you shapes. The Lewis dot structure just shows you the connectivity of the atoms, the lone pairs, the bonding pairs, stuff like that. So if I draw a Lewis dot structure like this is perfectly fine for a Lewis dot structure. So it may look like, in the Lewis dot structure, it may look like that these are 90 degree angles because that's the way I drew it. But VSEPR theory, if you use VSEPR theory, then the VSEPR theory will tell you what the angles are actually, even though you may not draw them that way. And you don't need to draw them that way. So here's my Lewis dot structure. I need to put the lone pairs in for my fluorine atoms. So each fluorine gets 3 lone pairs. Okay, and so here's my BF3, my boron trifluoride. Okay, so here I have 3 electron groups. So they're all bonding groups. I have no lone pairs. I have 3 bonding groups here. So the total number of my electron groups is 3. So in this case, whenever you have 3, these electron groups, again, want to be as far apart as possible. So just like in my analogy with the 3 arch nemesis, or the 3 mortal enemies, so they're going to want to move away from each other as much as possible. So then you'll get the pi figure. So these guys are going to be more like this. So you have boron, and you have fluorine, and then of course fluorine is going to be, they're going to move down here. So this is what it looks like really. So the bond angles are going to be 120 degrees each. So 120 degrees all around. Because we have equal bonds. So we have equal bonds here, same atoms, equal bonds, far apart as possible. Here as well, equal bonds, same atoms all around, so they're going to spread around equally. And so again, this the name of this shape is going to be trigonal planar. So you have trigonal planar molecule. And the reason it's trigonal planar is because you have three, right? You got three atoms or three bonding groups, and all of them are in the same plane. So if you connect these together, looks like a triangle, right? You got a triangle, and all of the atoms are in the same plane. So you can imagine the atoms in the same plane of the board. So it's in the same plane. So trigonal planar. So anytime you have three electron groups, whether they're bonding or non-bonding, the electron group geometries, that's what we're focused on for right now. The electron group geometry is trigonal planar. Okay? What if you have another molecule? So if we do CH2O. So CH2O, if I erase this, let me erase this. Okay, so here my carbon, so the Lewis dot structure for this is going to be this right here. So here's my Lewis dot structure. Again, I could have drawn the H's like straight across. That's fine too. The position of these with respect to each other is not really important for your Lewis dot structure. So again, I have three electron groups. I have the double bond here. Remember, the double bond is treated as one group, not two groups. So I have one group in the double bond, and I have a group for each of the single bonds with the hydrogen. Okay, so I have three total electron groups, no lone pairs, so that I don't have anything to count there. So the total number is 3. So 1, 2, and 3. So again, if I have three electron groups, the electron group geometry is trigonal planar again. So here we said the angles were 120 degrees. That's an ideal angle. So whenever you have all of your atoms are the same, all of the bonds are the same that are bonded to your central atom, then you're going to have the ideal angle, which is going to be 120 degrees for your trigonal planar, 180 degrees for your linear. Now, there are going to be cases where you're not going to have the ideal angle. And in a lot of those cases, it's going to be where you don't have the same bonds, right? Or you don't have the same, or you don't have, how should you say, the same bonds or the same atoms bonded together. So if you don't have the same bonds, or if you have lone pairs, right? We'll deal with lone pairs later, but if you have lone pairs, these angles are not going to be the ideal 120 that you would expect. The reason is because in the double bond here, you have more electrons. You have more electrons in the group. You have more negative charge. And so that negative charge here is larger. And therefore, the repulsive force is going to be larger. So these electrons here are going to be repelling these electrons in these two bonds here harder than these two are repelling each other. So what happens is that another way to think about it is that the double bond needs more space. So it's going to be pushing the others away. So since this double bond needs more space, then you'll expect that the angle here between the oxygen and the hydrogen here, this angle here, is going to be greater than 120, or I should say, let's see, so it's going to be, so greater than 120 degrees. So same for this one as well. This one's going to be greater than 120 degrees. And this one here, since they're being pushed closer, this one is going to be less than. This is going to be less than 120 degrees. Okay, so this will not have the ideal angles because of that double bond, right? These are going to, because they're all single bonds connected to the same atom, these are going to have the ideal angles, right? So there's no difference in repulsion between the bonds. So that's your 3 electron group molecule. What if you have 4 electron groups? Okay, so if we do 4 electron groups, so let me erase this. So so welcome back. So now I'm going to go over 4 and 5 electron group shapes. So if I'm going to continue with my analogy of the mortal enemies, then what you could do is, again, we're going to have our 3 mortal enemies, right? So here, and then we have one here, and again we had them at 120 degree angle from each other, so they're perfectly away from each other. Now, what if I add another mortal enemy onto the globe? So what if I take, this is my mortal enemy, and I put it right there on this face of the globe. So it's right here, and then they're kind of sticking out this way. So all 3 of these guys are going to be on, let's say, the equator. So let's say we're looking down on the Earth. So right here is the North Pole. We're looking down on the North Pole, and so here's our 3 mortal enemies, and I put one smack dab. So here's another mortal enemy right at the North Pole. So now, if this guy is on the North Pole and these guys are on the equator, then they're going to be 90 degrees away from each other. And then on the other side of the globe, there's no one there. It's open space. So you've got like 180 degrees on all sides. So if I put this guy right here, then the expectation is that since they don't want to be as close to each other, they want to be as far apart as possible. So since they got all this space on the other side of the globe, all 3 of these are going to move away towards the back or towards the bottom. If we're looking down from the top, so if we're looking down onto the North Pole, then these guys are going to be moving south or like behind the board from our perspective. So then these guys are going to move down a little bit. And so then when they move down, they're getting closer to each other, but they don't want to get too close. So they're getting farther from this one, but closer to each other until there's an equal distance from everyone. So everyone's as far apart as possible, equally distant from each other, and then that's where they stay. So what that's going to look like, it's hard to draw that because it is a 3-dimensional figure on a 2-dimensional board, but I will try my best. So if I draw my molecule, so let's draw the molecule, our generic molecule with the B in the center. So that's the same as having B in the center of the board, or this is my globe, and now I'm going to look down from the North Pole here. So I'm going to put an A here. So A is bonded there. There's my North Pole, and then I have the others as well. So in the next video, I will continue with this. With these other shapes. So stay tuned for the 3rd part.